Can you unmute your mic? Ma'am, your mic is muted.
All right. Yeah. So now, if I have, okay, if I have this, what was I writing? Yeah. So if I look at this column, 1, 0, okay? 1, 0, if I change one bit for this column, if I'm changing this, I'm changing 0, I'm making 0 to 1, okay? This particular bit I'm changing. This I can write as 1, 1, right? One bit change. I'm talking about if I'm changing this 0, it becomes 1, 1. On the other hand, if I'm changing this 1 to 0, this will become 0, 0. So it is connected, logically connected from this end to end connecting is there, okay, logically. That is why I can group 1, 0 with 0, 0. Actually, 1, 0, if I have a bit change, I can come to 0, 0 also. Got it? So that is why this grouping happens this way. Okay, this is logical adjacency. This is the term we use for that. Okay. Now, we were doing some examples. How many did we do? 2. Okay, all right. Okay, so now let's look at this question. My function right. Now, every time I'm not going to write the value in this corner. It is like initially we wrote, okay, today I will write in the first one, I will write it's 0, 1, 2, 3, 4, 5, 6, and 7. Okay. But you're supposed to know it. So now, if I'm going to write the values, which all min terms are true, this is 0 is true. So I put a 1 there. 1, 2, 4, 6, and 7. Now, what all groups I can form? I will make, okay, let me make one group. This can be a group, is it not? Okay, so that means I will write for each group I form, I'm going to write the corresponding product term and then move on. Okay, so this will be in these two, A is changing because the columns, both the columns are involved. I mean, both the rows are involved. So A is changing. What is not changing is C bar. Okay, plus another group, I can combine this, is it not? So that becomes, here A is, this row is same, so it's A, and what is B is not changing. Okay, B is 1, so plus I group this. Here A, the row is the same, so I have the value of A is A bar, okay, 0. And here B is not changing, but B is B bar. All right, okay. Now we are not looking at whether we can, further combine this and all. This is what you get from the K map. Okay, we are looking at what we get from the K map. Okay. Now, in the K map itself, we have something called we have another kind of a function like this. I will just draw this. Later we will look into this also. If I have a function like this, I'm sorry. Now this kind of a function, is it possible to combine this? This is not, it's not possible to combine. Okay, so now if I just write the minterms corresponding to these and see what it is, just to figure out what this function is, if I write it, it is going to be 0 and 1. Now I'm writing for this second, this one. Okay, this is going to be A bar B bar C. Okay, A bar B bar C plus this one is A bar B C bar plus this is A B bar C bar plus this is going to be A B C. Okay. Now this, if I look what this function is, this is, now let's see what I can combine. If I take A bar, I get this in these two, I will get A bar, I will get B bar C plus BC bar. In the next one, if I take A, I get BC bar plus BC. Okay, I'm combining these two. Oh, sorry, B bar C bar plus BC. All right. Okay. Now, what is this? Now, what is this function? Do you know something? That's XOR. Okay. And this is XNOR. That means XOR bar. Okay. So I can write this as A bar B XOR C plus A B XOR C bar. Okay. I'm writing it like this. Now, again, I have, this is again an XOR, is it not? If I take B XOR C as X is equal to X, I can say it's A bar X plus AX bar. So that is again another XOR gate. So this is A XOR B XOR C. This is actually sum for if you have a full adder, but that we will discuss again later. But what I wanted to tell you is that, so that means an XOR function cannot be simplified using K-map. Okay, XOR is a case of a function which we cannot simplify using a K-map because there is no possible way in which I can group this, as you can see the minterms written out here. Okay, now we have something called don't care conditions. Don't care. So as the name suggests, don't care means whatever, irrespective of the value of these, there are certain inputs. A function has certain inputs whose output is irrelevant. Okay, whatever is the output for certain combination of inputs, we do not care. So it's called don't care. Okay, an example of such a circuit, like if you have a circuit like this, not a circuit, I will just draw a truth table and show you what it looks like. This is a 4 variable K map. We'll come to this, but here, so don't care is marked by X. Okay. So now if I want to group it, I can actually see I have 3 ones here. Okay. Instead of grouping like this and like this, I can actually use the don't care to make a larger group. So I can consider don't care as a 1 because it's a don't care value. It can be either 0 or 1. We do not mind. So we can use it to make larger groups. Okay. So this is not how I will group it. I would group it like this. So but this it is not necessary that I have to group every don't care. If I have a representation on a Karnoff map with don't care values, it is not necessary that every don't care condition has to be used in grouping. Okay, wherever I can maximize my group, only there I will use it. So that is what a don't care is. So a function has certain input combinations for which the output value is irrelevant. Such input combinations are called as don't care conditions. Okay, an example of that is binary coded decimal. So here I have a binary representation for each digit. Okay, each decimal digit. Now, how many decimal digits are there? I mean, digits are from 0 to 9, right? So if I'm going to represent them, 0, 1, 2, 3, 4, 5, 6, 7, 8. Let me write a little. I'll write it here. 0, 1, 2, 3, 4, 5, 9. Okay. So now I need to use binary representation up to 9. If I need to go, I use 4 bits to represent. Okay, if I need to represent up to 9, I need 4 bits. Okay, so my 0 will be 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1. Okay, so by that, by using these 9 combinations, I have represented all the decimal digits. But I still have some more combinations in this binary pattern, right? Because I'm using 4 bits, I can have a total of 16 combinations. I've used only 9. The remaining 6 are called don't care. Okay. The remaining 6 would be, my don't care would be, after 1001, I have 1010, 1011, 1100, 1101, 1110, 1111. So all of these are my don't care combinations. Okay. Is that clear? Don't care concept is clear. Okay, now let's do some Karnaugh map simplifications using both minterms and don't care. Okay, combination. So if I have a function which is written as okay. Now this means I have a function which has a combination of these true minterms. These are the true minterms that I've written here. And this means these are don't cares. Okay, this sigma phi means these are don't cares. So these are the positions where the don't care I can put x. Okay. So now this is like going up to 15 already. So that means what we already did was a 3 variable Karnaugh map where we could represent up to 8. Right. Now we will have a 4 variable Karnaugh map. So we will have 4 columns and 4 rows. Okay. It's a little big, no, that's okay. Okay. So now 0, 0, 0, 0 means 0. 1, 2, 3. This is 4, 5, 6, and 7. Now where is 8? What is the combination for 8? What is the number for 8? 1, 0, 0, 0. So where is that? The bottommost. Okay. So here 8, 9, 10, 11, 12, 13, 14, and 15. All right. Because here also we have this representation because now it's become 2 bits even in your rows. So you have that 1 bit change. So we have 1, 1 here and then 1, 0. Because of that, 8, 9, 10, 11 comes here and above that you will have 11, 12, 13, I mean 12, 13, 14, and 15. Okay. Now which all values have 1? So 1 is 1, 5, 9, 11, 12, then 13. Okay. The rest are don't cares, which all 3 is a don't care. So I put an X there. 10 is a don't care. 14 is a don't care, 15 is a don't care. All right. So let me group. So what groups are possible? This is one group. All right. Yes, that is a group. So let me write first. F is equal to, when I group all this, now here what is constant? The rows are changing, right? This is a single column. So it will be C bar D because 0, 1 is coming in that column, C bar D plus. Now, another grouping I'm grouping like this. Right. All right. I can group it that way also. So in this, what is not changing in these two rows? If I see 0, 0, 1, 0, that means B is not changing. B is 0, that means B bar. And in these two columns, D is not changing. D is 1. So plus. Now one more group I will form because my one is left out. One is left out. I want to make a big group as big as possible so I can take this whole row. Is it not? Because I have don't cares there. I can group all of them. So now this will be AB because the row is the same but the column is changing because we have all the 4 columns coming in. Okay. Is this clear? I hope so. Okay, now let's do one more question like this. Yes, I will just go. Yeah, tell me.
Couldn't you have taken the right four, bottom four square x, y, z, and one?
This one,
Yes.
for this particular one, you're saying. We could have done that, but we will try to do it. We will not try to maximize the number of don't cares we use. We'll try to form a group where we have more number of ones already on our in the Karnaugh map, the midterm, and then we will take one more additionally or two additionally. It's not like we leave out one. So we try to group using the midterms which are available. Okay. In addition to that, we will add one or so that will not be the most efficient way of grouping. You can group that way also, but that is not the effective way. Okay. Okay. So first one is 0, then 7, 10. 10 is going to be, this is 10. Okay. And then the don't cares are 2, 5, 8, 15. So let's group. This is one group, right? That one I cannot group any other way. There is nothing near it. So I use that don't care and group it. All right. So F is equal to, the first term is in this, the row is constant where row is 0, 1. That is A is 0. So that is A bar and B is 1. And in this two columns, what is not changing? D, right? D is 1 in both. Plus, what will my other group look like? These 4 together. 4. What is the doubt? Why? I told you, this corner to corner also is adjacent. So it's like having them, if they were on the middle of this thing or of this map, the same way it will be when they are at the corner also. Okay. They are connected end to end. Like you roll a paper or something, no, the ends are connected. Okay. So this end is connected to this end. That means they can form a group. So now in this, what is it going to be? This is going to be, what is not changing in the rows? B bar. And in these two, D bar, right? In these two, if I see, D is not changing and it is 0, so it is D bar. Is this clear? Something. This one, did I write correctly? 0. No, this is not A bar, no, this is, that's correct. Okay. This one. Yeah, you can group like that also. Okay. If you are grouping, on the other hand, no talking. If you're grouping this way, okay, instead of this, if you're grouping like this, then instead of this term, you will have B, I think B, C, D, because the column is C, D. Okay, so this term changes. So here we have the option of grouping because you have multiple don't care bits. Okay, so sometimes we do not group in the same way. So don't care, when don't care comes in, you can, in this, whichever way you group, it is the maximum. Only two you can group. So I group it either horizontally or vertically. Still, I get a group of two only. So it's up to you which way you group. So whichever way you group and write, the answer is acceptable. Okay. Now, let's learn a new term called prime implicant. It's related to Karnaugh map itself, prime implicant. Now, suppose if I have a Karnaugh map, okay. Now, see this particular case, okay, this one, I can group this like this, okay, this one, these two ones I can group like this. These two ones I can group like this, okay. Is there any other way I can group this one, the one on top? No other way. I have to group it with the one below it. Even this one also, I have no other choice. I have to group it with the one below it. What about the one in the center? This one, I can either group it like this or I can group it like this also, right? I have a choice there. So when a prime implicant is a product term that is obtained by making the maximum possible cube, okay, the largest cube that you can form for that product term that is obtained by making the largest possible cube or group for a min term. Now, which min term am I talking about? I'm talking about this min term. If this min term, if I have to, the largest group I can form is this. For this min term, the largest group I can form is this. Okay. So they are all called prime implicants. The group that I form is called a prime implicant, if that is the only possible group for that min term. Okay. So if I have a square like this and I have a 1 here and I have a 1 here and a 1 here, I have no other choice other than grouping it this way. Okay. Okay, but this one I can group with this one also, right? These two ones I can group. So only this one doesn't have a choice, that I have to group it with the one below it. So that kind of a group which I form where there is no other choice, we call it a prime implicant. Okay. So, and that should be the maximum size of the group that I can form also for that particular min term. Here it is 2 by 2. I will show you other examples where we have larger groups as. So is it understood what a prime implicant is? So any kind of group that you can form which where there is no choice that you have, it is called a prime implicant. It is called an essential prime implicant. Okay, actually. Where you don't have choice, you call it an essential prime implicant. Now, in this case, where I had this one, I had a choice. So I can group it this way or this way. So I call it a non-essential prime implicant. Okay, I call it a non-essential prime implicant. So a prime implicant is nothing. Yes. What kind of a group is that? Only one bit change is possible, right? That's why we group either a single column or a single row, right? We don't group. See, if I have like this is what I drew. You're saying this, and this I can group, you're saying. How many bit changes happen? Our grouping, see, we can group only as groups of 2, 4, 8, and 16. Okay. Powers of 2. Not any number we cannot group. Okay. So those are certain rules that we have to follow while grouping and minimizing. All right. So I can't group if I have 3, 5 all nearby. I cannot group them together. I have to group either in groups of 2, 4, 8, or 16. Okay. So, what was I saying? Ah, no, this is not your doubt. Okay. So now suppose if I have a table like this, okay, and I have this, I can call as a prime implicant. Okay, suppose I have only these 4 numbers. When I group them together, this is a prime implicant. Now this I can actually, if I want, I said I can group as 2, 2, 2, or 4, right? I said I can either make groups of 2, 4, 8, and so on. So suppose if I group like this is a subgroup, right, within this particular group. This I call an implicant. This is called an implicant. If I have a group within a prime implicant, so a subgroup within a prime implicant, you call it as an implicant. But you don't have to focus on implicant. We are looking only at prime implicant. So always our goal is to maximize the group that we have in powers of 2. All right. So now if I have, okay, now I have, now tell me which are the prime implicants in this. Okay, I will just draw a Karnoff map. Okay, what are the groups I can form? The center I can group everything. Okay, and corners also, yes. Yeah, edges, everything I can group. Good. Now, what kind of prime implicants are they? Every group is a prime implicant. So, is it a essential prime implicant or a non-essential prime implicant? How many support essential? Still everybody's a little confused. Essential means I cannot group it in any other way. These 4, can I group it with anything else? Not possible. So this is an essential prime implicant. What about these 4? I cannot group it any other way. Maximum group. I'm talking about the maximum group is not possible in any other way, right? These 4 also. So this is also an essential prime implicant. Okay. So if it is not possible to group in any other way, it becomes a essential prime implicant. Now, this I call P1. Okay, this group prime implicant I call P1. Another prime implicant is this, that I call P2. Then one more one is to be grouped. This I call P3. All right. Now, are these essential or not? Which of these are essential? Which are not essential? P1 is essential because P1 covers what is non-essential. P2 is not essential See, P2 is covering these two. These two. Is that those two one? Is it being covered by any other group? No, right? Those two one is not being covered by any other group. So that means P2 is also essential. Okay, I cannot cover it with P1 or P2. No other prime implicant is covering that these two ones. So P2 is also essential. What about P3 now? P3 is also essential because P3 covers this one, which is not covered by P1 or P2, right? And P1 covers these two, which is not covered by P2 or P3. So everything has one or more min terms, which is not covered by the other groups. So that means each of them are essential. Is there any doubt in essential implicants? Okay. If you have any doubts, you can ask. That's why I'm telling. Yes. This one. Which first one? This one. I want a maximum group. No, it's possible for me to group it as 4 because neighboring also I have 2 ones. So even though I can make a group of 2, I try to make it a group of 4 for better minimization, because the moment I make it a larger group, I will be able to knock off more number of literals or variables from that expression. So if I group it as 1 and 1, as you said, Shreyansh, this will become just an implicant. It is a part of a bigger group. Okay. Yes. I can't hear you. See, P1 covers these 4. Okay. In that, these two are not being covered by any other group. Okay. What is P2 covering and what is P3 covering? See, if I have this, I'll draw it once again. 1, 2, 3. Okay. And I have written 1, 1, 1, 1. Okay. Now this is my P2. Okay. This is P2. This is P3. Now this whole thing is P1. Okay. P2 and P3 are not covering these two. Right? Right? That is not the maximum I can form. I can take 4 and form a bigger group. I always try to make a larger group if possible. I don't want small groups. Okay. If possible, I will make a group of 4, if not 2, if it is available. Okay. If I have neighboring ones, then I will make it as a group of 4. Okay. We never try to make small groups. We always try to maximize our group size in powers of 2, not 3, 5, 6 and all. 2, 4, 8, 16, so on. Okay. Now, if I have a cube like this and all these are 1, what will be the function now? Function will be 1. Okay, the moment I can make the largest group, which is the size of my Karnaugh map itself, then this function is equal to 1, because this is the group I form. All my variables will be knocked out. Because see, as I combine, when I combine two groups together, if it was 3, I had shown it in the previous page somewhere when I started off. Yeah, so I was saying that in this Karnaugh map, I showed that each min term is a bar, b bar, c, a bar, b, c. When I combine them using this, it becomes a bar, c. From 3, it has become 2 when I formed a group. Same way, when I make a bigger group, one more literal will be removed. So when I group it all together, that is the entire Karnaugh map I can group as 1, then the function is equal to 1. Okay. So this is the thing. Then now I have a Karnaugh map for, this was all for min terms. Now max terms, product of sums. Okay, so that means my function is written like this. Oh, not this. Wait. Pi. No, wait. Function is written like that only. Let me say. function is written like this: 1, 4, 5, 6, 11, 12, 13, 14, 15. Not pi. This sigma means this is min terms, right? From this, can I write what will be the max term? All the false conditions will be for max term. Okay. So that means wherever this is 0, 2, whatever is not there in this min term combination, all that you will write in your max term. So 0, 2, 3, 4, 5, 6 is there, 7, 8, 9, 10, right? 11, 12, 13, 14, 15 is there. Okay. So now I need to have a 4 variable Karnaugh map again. Okay. So now for a max term, 1 is not the term that we use. We use 0 for max terms. Okay. Because we were always using, when a is equal to 0, we take it as 0 is taken as a, and 1 is taken as a bar for max term representation. So here now in 0, I will put 0. 2, 3, 7, 8, 9, 10. Okay. So let's group. Well, right, f is equal to, now when you write also, you will not write as product, you will write as sum. Okay. So 0 means the uncomplemented form. So in these two, b is 0. So b plus, in these two, d. Okay, b plus d. Now another group I have is this. Okay. So I can write that is a plus C plus D, I think. No, C bar plus D bar, right? Because this is one column where C and D is 1 means both are complement because it's post form. Then the last group, this is my group. Here A bar B plus B plus C, right? A bar plus B plus C. So this is how you will represent. If I give you a question to find the function or a reduction using Karnaugh map where I have given a max term, you have to use zeros in the positions corresponding to the max terms and group them. Grouping is the same, but when you write, it will be like product of sums. That is the form you have to write. Okay, in max term form, you have to write it. All right, now, okay, so now we say that, I mean, I told you about okay. Now POS and SOP are equivalent. Okay, we say they are equivalent. Let's just prove it with one example. When I write it as POS or SOP, it should be the same function, means it should reduce. When I reduce it, I should get the same thing in both ways, whether I use a min term or a max term. So let's see one example. In fact, this I had done halfway, I think, last class, but I didn't finish it off for you. Okay, so this is one group. I am just going to group B bar, A B bar is there, so I group these two. Then in this I have A B, so I group. Now to group this, I can use A B. I add one more A B C bar, which I group with this. If you remember, I had done it last class also. Okay, so the reduction, if you remember, it is A. Okay, yeah. The first two, when this first and the last terms, when I group, B C bar, I take A plus A bar plus Here I have AB bar, C bar plus C plus AB C bar plus C. So I get this is 1, this is 1, this is 1. So BC bar plus AB bar plus AB, which is equal to, again I can combine these two. So BC bar plus A, B plus B bar plus B. So I get BC bar plus A. Okay, this is my function, and I had written the truth table also for you. You need not repeat if you already have noted it down. You need not repeat 0, 0. Okay, I'm only writing up to 4 because I'm just writing the conditions where it is false. Okay, we already wrote max term, we have written. So 0, this you will get 0 if I implement this function. This I will get 0, and this I will get 0. Okay, now if I want to write it using max terms, I say that I can take all the conditions which are false. Okay, in order to represent the same function using max terms, we have to take all the points where the function is false. Okay, so these are the 3 cases where the function is false. So I will write it as my f bar, because it is where the function is false, is equal to, this is one case where it is a bar b bar c plus a bar b bar, no, a bar b bar c bar, a bar b bar c plus a bar bc. Okay, this is the thing. Let me go forward and apply De Morgan to this. Okay, so f is equal to, if I apply De Morgan to, okay, I'll write it here once again. A bar b bar c bar plus a bar b bar c plus a bar bc. So if I apply De Morgan, it becomes a plus b plus c, a plus b plus c bar plus, no, sorry, no plus, a plus b bar plus c bar. All right. Now, if I have to group this, how can I group it? I have only three terms, right? I mean, 3 terms are there. I want to group and minimize. So if I have to group 2 terms, I have to have totally 4, right? If I have to group. So I can add, I mean, I can replicate one of these terms again. Which term should I replicate? I will look what is common. Now, if I look at these 2 terms, a plus b is common. If I look at these 2 terms, a plus c bar is common. So that means this middle term is the ideal one to replicate. So I will add, I will put that also, a plus b plus c bar. All right. So now if I write this, now I'm going to split it into 2 parts. This is going to be a and this is going to be b, because I have to do lengthy this thing. So I will, let's find out what is a. Okay. Now a is going to be a plus b plus c into a plus b plus c bar. This will be, you can start multiplying, you can do a plus. Okay, we got this. Okay, when I multiply with each term, okay, I do the dot product with each. Okay, I get this. Okay, when I do and. So now a means what? A plus AB. There are two ABs. So I can write as a single AB, right? AB, x plus x is x. So plus AC. BB is B. BC plus AC bar plus BC bar. CC bar is what? 0. So I can cancel it out. Now, let me combine these two. This becomes A, sorry, A, I will get 1 plus B, right? So, yeah. So I get 1 plus B, which is 1, plus AC. Same way I can take B here, B common if I take 1 plus C. C bar, A plus B. Okay. C bar, A plus B don't do. Let's wait. Don't do C bar A plus. We leave it like that. Let's see whether we can combine anything else. BC and BC bar to make what? Now you want, okay. Okay, fine. So let's do that. That was okay. Okay. So you want to combine AC and AC bar, right? So I get A, C plus C bar. Then BC and BC bar I get C plus C bar. So this is 1. This is also 1. So I get, this is what, this is again 1. A plus B. Something is missing somewhere. One AC is there, right? This one, no? That B is also there. Okay. So B is there, and then this AC is also there. No, AC already combined. AC already combined, right? So finally, what you got? A plus B. Yeah, that's it. Yeah, A plus B. That's what we get. A plus B. Okay. Same way B part do. B part, this one. Come. So I'm not doing that part. If I do, I will get A plus C bar. Correct. So now that means my function f is equal to A plus B, A plus C bar. Right? This if I write AA plus AB plus AC bar plus BC bar. So this is A plus AB plus A. So I have AC bar plus BC bar. This is A plus AB will become A 1 plus B. Leave it like this, wait. So this becomes, so A plus AC bar plus BC bar. Now I combine this. This becomes A 1 plus C bar plus BC bar. What is this? Did I get the same thing as my min term I started from? Okay. I started with my min term BC bar plus A, if you can see. Okay. Now I wrote it, I took the false terms in my expression and I wrote it in my max term format. Right. I took the complement of that. I did all these things. And then if I try to combine what I got finally, I can come back to the max term itself. So that is why when I take the negative cases of my truth table for max term is equivalent to taking the positive cases when I represent it as min terms. All right. I was just trying to prove that both are equal. All right. Okay. Now, we also spoke about something called functional completeness. Okay, functional completeness. Remember that some of the gates, some combination of gates can be called as functionally complete, which all NAND we could call that way, NOR we could call. Then we had, yeah, and OR together becomes not NAND and not, and not together. Same way OR and not, right? So then with XOR with the condition becomes a NOT gate and all that we saw. Now there's one more case we can talk over there. It's called a multiplexer. Okay. A 2 to 1 mux. We call it mux. Another word is mux. Okay. Now there is one functionally complete set which is 2 to 1 mux 1 comma 0. Okay. Now mux is a logic element which if I have two inputs, these are two inputs, I also have something called a select signal and I have an output f. Okay. Now f is equal to as bar plus bs. Okay. This is what it represents. Okay. The function that the mux represents. So now if s is equal to 0, what happens to this function? F is equal to S is equal to 1. So A dot 1 plus B dot 0. That B dot 0 is 0. So A dot 1 is A. So whenever S is 0, my output will be A, the first input. Now when S is equal to 1, F is going to be equal to A dot 0 plus B dot 1. So this will be B. Do you understand? Yes or no? Who all have not understood? Yes. See, I have a logic block which has two inputs, A and B, and not only two inputs, there is something like a control bit S, like we talk about control. Same way, this is called a select input. Okay, S. Now my output is dependent on what value the select bit takes. If select is going to be 0, I applied select is 0. This is a function that it represents. My output is going to be AS bar plus BS. So if my S is 0 means S bar is what? 1. So A and 1 will be A. B and 0 will be 0. B and 0 is 0. So this term is going off. So my F is going to be A. So when select is 0, my output F is going to be A. If S is 1, what happens? S bar is 0. So A dot 0, that is 0 itself. Or I mean, AND operation with 0 is 0, and then B dot 1. So it will be B. Is it clear? If you don't know what is A dot 0 and A dot 1 and all, I cannot help you now. What? F is equal to AS bar plus BS. That is the logic function that it performs. That is how it is designed. It is designed such that this is a function for which I am just showing it as a block. Okay, I can write it like this. I can draw it as gates also. Okay, so A and S, I have S here. I take the NOT and I give it here. And this S and B together, I give it to another AND gate and I OR them. I will get F. Okay, this is what it is. So how does it work? So what it does is that when S is 0, this input is driven to the output. If S is 1, this input is driven to the output. That is a function of a mux. And mux is usually used as a sub block in most of the bigger circuits that you will build as we learn. Okay. So now this is what a mux does. Now let's see how can I represent a mux. How can I realize other gates using mux? Okay. Realize a NOT gate using mux. So let's see how we can do that. Okay, so now A. Now I will fix my A at 1 and I fix my B at 0. Okay. Suppose if I fix my A at 1 and my B at 0. I have my select signal here, F. Okay. So F is equal to AS bar plus BS. That is a function. Now A is 1 means this is going to be S bar. B is 0 means this will be 0. Right? So when I fixed A at 1 and B at 0, what I'm getting is complement of S. Right? So that is like getting NOT operation. Okay. So that is why we say when I wrote the set, I wrote that 2 to 1 mux, comma 1 0, because I need to use this combination of A and B if I have to realize a NOT gate. Okay. So if I fix A at 1 and B at 0, then what my function would be? The complement of my select value. Then if I want to represent AND, so for AND what I do is that let me set A at 0. B is, I do not bother about the value of B. So then F is equal to AS bar plus BS. A is 0 means this term goes off. So this becomes BS. This means AND. B dot S, right? This is AND function. Same way, or if I want, or let me set A to 1. When I set A to 1, F is equal to AS bar plus BS. So now A is 1 means this is S bar plus BS. Okay. Now I can write this as S bar plus B by a law called absorption law. We already learnt it in class. That is like X plus X bar Y is equal to X plus Y. X bar plus XY is equal to X bar plus Y. Okay, this we have already done in class. You can go back and check. So that law is called absorption law. So using that, I am able to write S bar plus BS as S bar plus B. So when I write this is OR operation, right? I'm doing OR of S bar and B. So this way I realized OR and NOT, everything, all the basic gates I can realize using a mux also, 2 input mux. So that is also a functionally complete circuit. All right. Now some universal gate questions. Okay, I want like a 2-level and OR circuit is equivalent to NAND. Okay, this now once again last class also I mentioned De Morgan's law. Before I draw the circuit, De Morgan's law. What did we have in De Morgan's law? If I have A dot B the whole bar, that's equal to A bar plus B bar. So this is right, and followed by not. This is equal to A and B. I not them, and then I have the OR gate. Okay. Now this, whenever I have a bubble, this bubble, that means it is a NOT gate. Okay, wherever I have the bubble. So that means this I can actually change like this. Okay. Inverter, I clubbed it to the OR gate and I'm representing this one like this. Okay. So now this, what do I call this? This is a NAND gate, right? And that is the same as this. This is an invert OR. We had written it, invert OR last class. So NAND is the same as, it's equivalent to invert OR. Okay, now I have a function like this. It is AB plus CD. Let's draw the figure, I mean the logic diagram for it. So this is going to be A and B. I AND them, C and D also AND them, and together I have to OR. I get F. Okay. Now this is called a 2-level AND OR. That's what we mean, 2-level AND OR. That is, in the first level I am doing AND operation for various variables. It can be multiple number of gates. So I do AND operation. In the second stage or the second level, I do OR operation. So that's why it's called a 2-level AND OR. Okay, circuit. Now this I want to convert it into NAND. Realize it with NAND. So what do I do? What I do is that if I have to make it into a NAND, I need to invert, right? I invert after the first level, I put inverter out after the AND gate. Now, if you're doing math, okay, I'm writing 5 plus X and I'm adding 5. Okay, X is here, Y is here. If I have to equate this, if I'm adding 5 here, I have to add 5 here also, right? In math to balance the equation which I had. Same way, now I have just inverted here. So I have to add one more inverter somewhere. So here I come here, I add one more inverter. Got it? To nullify that effect, because I am adding it. I cannot simply add something to a circuit. So I add something at this end. So at this end, I add 2 more inverters. Now this has become a NAND. Right now, when I did this is a NAND. What is invert OR? Look up here, I have told invert AND is also a NAND gate. So I can directly replace this with NAND now. Got it? Did you follow? Anybody has a doubt in that implementation? How we had the AND gates. We tried to invert the output of the AND gates. When I do an inversion, forcibly, I have to do it double, 2 times, so that I can nullify that effect. So I inverted it here at the output of the AND gates. I inverted again at the input of the OR gates. So this became a NAND representation. And invert OR is also an AND. It's equivalent to an AND by De Morgan's law. That's what we saw. So now I can draw this as okay. Now it's become totally NAND gate representation. This is how you should convert a circuit. If I give you a circuit and say, okay, now you realize this only using NAND gates. So this is how you have to do. Now, I hope it is clear. If you have any doubts, please ask. Okay. Now, two level or AND is equivalent to, what will it be equivalent to? Nor. Okay. Okay. So now let's have a circuit. F is equal to A plus B dot C plus D. Okay. AB, BD. Okay. This is F. Now, here is the other De Morgan law, that is A plus B the whole bar is equal to A bar dot B bar. Yes. So this is OR followed by inverter. This is equal to invert. I have an inverted, I have A here, I have B here, I invert them and then apply it to an AND gate. Yes or no? Like what I showed in the previous slide. So this is NOR and NOR is equivalent to invert AND. So now based on this understanding, let's change the given circuit. So I invert outside the OR gate. So to nullify that, I have to again invert it. Okay. So this I can replace by a NOR gate again, because NOR is equal to invert AND. Right. From what I have drawn here, from this, I can deduce that. So I can replace it. So the final figure would be 3 NOR gates, basically. I'll just draw here. All right. Okay. Now there is one more circuit which I want you to convert to NOR. Okay, I mean not NOR, NAND, to pure NAND implementation. Some gates are already as NAND. This is the circuit. Start drawing. There is only one gate you need to convert, yes. To NAND, no? So I have the circuit like this. Okay. Now here, and then I again put one more. Okay, because this function is here. Now instead of this, if I put a NAND gate, this becomes some F bar. So I have to again invert it. This is like a NOT gate when I have a single input going to, single signal going to both the inputs of the NAND gate. So this becomes F again. Okay. So this was just a NOT operation that I did from. So this way, I will get the gate. Okay. Now, design of combinational circuits. So, what are combinational circuits? They are circuits whose output depends only on the present value of input. Like if I had, going back to the previous page, here if I have inputs A, B, C, D, and E, the value of this function will only depend on what value A, B, C, D. If I'm giving 0, 0, 0, 0, 1, this is going to determine what the output is going to be, right? The value of A, B, C, D, E at this particular instant. If earlier I had given the value as 0, 1, 0, 1, 0, that does not have any bearing on the output. So output depends only on the value, present value of the inputs. Those kind of circuits are called as, referred to as combinational circuits. Okay. Now there are certain circuits which depend on previous history of inputs. Like suppose, let's take a example. We have a traffic light. Here, traffic light on the roads. So you have the red, from red it goes to yellow, then it goes to green. Now, if the light is yellow at a specific instant of time, now will the red lamp glow or the green lamp glow will depend on what was the previous state, right? It is not going to be the same always. So earlier if it was green, then after yellow it's going to be red. On the other hand, if it was red before yellow, it's going to be green in the next stage. So it depends on the previous value of the input also. Okay, input output states are all dependent here. So those kind of circuits are called sequential circuits. So we need to have a memory there, which helps us to store what was the previous value. Okay, here it is just dependent on the present state of inputs, you get the outputs. So the common circuits, combinational circuits that we have are adders. Okay, adders, subtractors, all these arithmetic circuits, multipliers. Then we have multiplexers. We just saw a small one. We have larger 4 to 1, 8 to 1, and so on. So multiplexers. Then we have decoders. So many kinds of combinational circuits are there, which we will learn one by one. Okay. Now, when I say addition, you already know about half adder. That is where I can only add 2 bits. I cannot store a carry, or I cannot add a carry there. Like if I have 0, 0, 0, 1, 1, 0, 1, 1. My sum is going to be 0 plus 0, 0, no carry. 0 plus 1, 1, no carry. 1 plus 0, 1, no carry. 1 plus 1, 0, and carry is 1, right? This is like adding 1, 0, 1 plus 1, 0, 0, 1. Suppose if I add these two digits, it's okay. I get 0, I get a carry here. But if I'm using this kind of a circuit, I can only add 2 bits, right? I don't have a provision to add the carry that is coming in. So this kind of a circuit where I cannot add a carry over from a previous bit, these kind of circuits are called as half adders. So generally half adder is not a very practical solution or a circuit that we use, because it can be used only to add the LSB. Because in an LSB, I don't have a carry. I will only have 2 bits to add. But from the next bit onwards, it is possible that I have a carry. I can have a carry or not. I could have a carry. Carry could be 1 or 0, depending on what I'm adding in the LSB position. So half adder can only be applied to add these LSB positions without any issues. Okay. So for that purpose, for practical purposes, we use something called a full adder, where we can accommodate the addition of 2 bits and a carry as well. Okay. So now, before drawing the half adder, let me anyway draw the half adder and finish it off. So next class we can start with full adder. Yeah. So half adder, you know already. I have been saying this, I think, multiple times. If I write which are the true cases, it's going to be a bar b plus ab bar, that is a XOR b, and carry is going to be true only when a and b are 1. Okay, so if I have a block like this, which I call a half adder, My inputs are A and B. So A and B, if I XOR them, I get the output sum, and I AND these two, I will get the output carry. All right. Okay. Okay. Ah. Clap a little more louder. You people are so good in clapping. Thank you. Thank you. Actually, clap only is not enough. Next class onwards, bring chocolates, things like that. More motivation you give me. Okay. So, okay, you can leave if you want. Yes, online students can leave.